Okay, wait, I record this one. And then I think it's very short today. Okay, and next week we can move to the new topic. Okay, chapter 10, which is the application of the modifier of law, how to find the temperature or pressure from the bulb and as well as the dew points. Okay, how to calculate the flash composition from the flash calculations. Okay, but today is we will cover about the property change of mixings. Okay, so I hope no question about the previous example. I gave you also the solution for the tutorial, right? So I hope you can use as a reference to study the tutorial for this one. Okay. Actually, the solution is only for tutorial 1 and tutorial 3. Okay, for tutorial 2 and 4, so you have to just refer to the solution in tutorial 1 and 3 as your reference. Okay. Okay, so we move to the property change of mixings. Okay, actually, if you remember in chapter 11, we deal with the excess properties, isn't it? Okay, so as if the properties of the ideal solution. Okay, this is we use to calculate the excess properties for non-ideal solution. Okay, and each may be combined with the defining equation for the excess properties. If you remember, ME equal to M minus M ID to determine the excess properties. Okay, so M is we can define as G. Okay, gives energy, entropy, volume, as well as H, enthalpy. Okay, so if you look at here, this is the okay. Remember, this is for M. Okay, the actual, and this one is MID. If you remember from the chapter 11. Okay, both is all this from the chapter 11. Okay, but if we take this one, okay, as a delta G, delta S, delta V, as well as delta H. Okay, so if you look at here, what is become? Okay, and is become this equation. Okay, so if you look at here, so G equal to delta G mix. Okay, it's mixed already. Delta S mix, delta V mix, as well as delta H mix. This is for excess heat energy mixings minus RT. Okay, sigma sum of Xi log Xi. This one is for excess heat energy. Okay, as well as for excess entropy, volume, as well as enthalpy. Okay, so this one is molar defined as a molar of solution properties. Okay, mixing. Okay, no, this one is more solution properties for mixings. Okay, so mixings equal to M minus Xi Mi. So this one also can be Gibbs energy H. Okay, as well as entropy. Okay, so from all this equation, actually we can derive for the heat of mixing. So actually for the excess properties, okay, for mixing, okay, the delta M mix equal to delta M ID mix. Okay, so must be minus with ideal solution, so that we can get excess properties. So if excess properties is equal to 0, okay, so that means GID mix is equal to just RT, because this one is equal to 0. Okay, look at here. Okay, this one is 0, 0, 0, 0. This one is for ideal solution. Okay. Okay, so for example, for the ideal solution, if you look at here for the energy balance, okay, look at here, actually is Q delta H equal to 0. Why? Because it's ideal, not mixing. Okay, we didn't consider as there is any heat change. Okay, because it's ideal. Okay, if you consider Q minus W equal to delta H. Okay, kinetic energy, potential energy equal to delta H. Okay, this one. Okay, so we can just cancel out this one. Okay, neglect this one. So H out minus H in. Since this is ideal, okay, so actually is equal to 0. Okay, this is only occur for the ideal mixing. Okay, if you refer chapter 11, it's also 0. Okay, the enthalpy change. However, if non-ideals, what happen to non-ideals? Okay, So we have to find the delta H mixing because it's not equal to 0. Okay. So generally, how can we determine the outlet temperature? How to determine the composition? Okay. So this is how can we determine delta H mixing? Okay. So delta H mixing is can define also is from the previous equation. Okay. Delta H. Okay. And you remember, so to H. Okay. Minus Xi H Hi. Okay, this is delta H mixing. Okay, enthalpy change when pure species okay are mixed at constant temperature and pressure for 1 mole of solution. That's with heat of mixing. Okay, so we can calculate from the enthalpy of solution, or it's almost similar like heat of reaction. We calculate from the heat of formation, right? So we can calculate also similarly. Okay, from the heat of solution or enthalpy of solution. Okay. So let's move. How can we calculate this delta H of mixing? Okay. So another example for the non-ideal solutions. This one, solution A plus B. Okay. Flow pipes. Determine the stream over the enthalpy. Okay. So this one we can calculate from the heat of formation of the solution and heat capacity of the solution. Okay. This is one of the examples. Okay. Just as general. Okay, almost similar like the heat of reaction. But generally, heat of solution or heat of mixing is actually the energy is smaller than heat of reaction because it's not involving the rearrangement of the constituents atoms. Okay, so generally it's much lower. Okay, but energy, yes, it's changed when you mix between two solution. Okay, for example, solid in liquid or gas in the liquid, definitely is going to be changed. Okay, so heat effect of mixing process. Okay, two ways to solve the energy balance. First, by using enthalpy of solution and use heat of mixing. Okay, this is the heat of mixing. This is the definition of the heat of mixing. Okay, so we can refer to diagram. Okay, so if you want to calculate, for examples, heat to calculate how much solute soluble in solution. Okay, so you can calculate from the figure 12.17 or 12.119. Okay, this is the figure. Okay, for example, if 50% of H2SO4, okay, you mix X around 10 degrees C. Okay, so around 10 degrees C, and then you can determine the heat of solution. So this is 10 degrees C, and then you can determine. Okay, so this is for H2SO4 in H2O. How many percent? Okay, so you can calculate. This is the heat. Okay, should be in kilojoule. Okay, kilojoule per kilogram. Okay, you have to remember the unit. Okay, so and then
Doktor,
ya,
graf ni untuk H2SO4 je.
yang ni H2SO4.
Kalau graf yang kalau HCl dia ada graf lain lah.
Dia ada graf lain lah. There's gonna be different graph. Okay, so you can refer to any engineering book, or we can calculate actually from the heat of solution, heat of formation of the solution. Also possible. If not, we cannot determine from the graph. Later I will show you how to calculate. But generally the example is only for lithium chloride. But for the other components, okay, solute in solution, I will show you which data you can refer. Okay, I just refer from, I just download actually from the data is available in the internet, luckily. Okay, this one is for H2SO4. Okay.
Yeah.
Okay, this one is for NaOH. Okay, see, it's different, right? So actually it's different. It's not gonna be similar. Okay. For example, 50% of NaOH at 85 or around 90 degrees C, and then you can, okay, 50 degrees C. Okay, around this one. Okay, 85. Okay, and then you can read how much the enthalpy of solution. Okay, so it's easy, right? This one. Okay. Okay.
Kira teh.
So that is for the delta H mixing. Okay. Okay, let's see the example. A single effect evaporator concentration 10,000 pound mol, okay, per hour, okay, of 10% by week, aqueous solution and NaOH to 50%, okay. The feed enters at 70 degree Fahrenheit. The evaporator operates at an absolute pressure 3 inch mercury, okay, and under this condition, the boiling point of a 50% solution NaOH, okay, is 190 is 190 degree Fahrenheit. What is the heat transfer of in the evaporator? Okay. So if you look at here, okay, what you have to do is generally we can draw the diagram, or if necessary, if there is a change in the mixings, okay, you have to draw the hypothetical part. Okay, also possible. Okay, so if you look at here, the feed is actually is 10,000 pound more. Okay, with the 10% of NaOH. Okay, at 70 degrees C. And this one M1 we consider as a M1. This one M2, and this one M3. Actually, we have to determine M2, M3, and M2. Okay. Once you do the mass balance, okay, for the NaOH, okay, you learn already this one. So you can calculate M3 as well M2. Okay, this is the value. Okay, so this is the value. Okay, and then what you have to do is to do the energy balance. Okay, so if you do energy balance, okay, since this is a no reaction, okay, no reaction, that means no generation, okay, no accumulation. So H out minus H in. Okay, so the which is leave the reactor. Is it reactor? Not reactor. This is just separator, evaporator. Okay, no reaction. Okay, so this is the component that leave the evaporator, and this one is enter the evaporator. Okay, so how can we read from the diagram? If you remember this one, the conditions. Okay, M3 we know, M2 M3 M2 also we know, we calculated already M1. The problem is the H. Okay, how to calculate H? Okay, which is the enthalpy. Okay, so M3 H3 is actually is the steam, squator steam. So that you can refer to the table. Okay, so if you refer to the tables, okay, we can calculate here. Okay, if you refer to steam tables, I think it's page, I don't remember. But this one, the unit is BTU per pound mass. Okay, and your book is actually is SI unit. Okay, so if you refer to the page, I think it's around, what is the, this one is around, wait, okay, so this one 190 degree Fahrenheit. Okay, I think this one is around what is the temperature, 190, I don't remember. Okay, I think it's around 80 degrees C. Okay, around 80 degrees C. Okay, 81. Okay, 81 degrees C, I think. Okay, this one around 81 degrees C, and the pressure is around 10 bar. Okay, or 10 kilopascal. Okay, this one is 10 kilopascal. You have to convert. Okay, 10 kilopascal. I think this one is 81 degrees C, I think. Okay, please check again your how to convert from degree Fahrenheit to degree C, because you have to refer to the SI unit of the tables. So you can calculate actually. Okay, so you can calculate. This is around 2000 something, 2600 something. So when I converted into the BTU per pound mass, how to convert this one? Okay, from I think the unit is kilojoule per kilogram, right? Okay, so you have to convert to BTU per pound mass. Okay, so you can get 11446. Okay, so how about this one? Okay, 215. Okay, 215. How can I determine this one? Okay, So if you refer to figure 12.19, okay, if you refer to figure 12.19, okay, 12.19 is actually is for the NaOH, okay. So NaOH, if you look at here, M2H2, right? M2H2, this one 50%, this one 190. I think it's around 88 degrees here. I think this one 88 degrees. Sorry. Okay. So if you look at here, 50%. Okay, let's see. We refer here. Okay. We look at the diagram for the NaOH. Okay, this one. Okay. So 50%, and then for the, I think it's around here. Okay. Okay. Around here. Okay. Around 500 something. Okay. 500 kilojoule per kilogram. Almost there. Okay. 500 kilojoule per kilogram. Okay. So this one, it should be just change to this one is actually is not this one. 250. Yes. 500, okay, kilojoule per kilogram. Okay. So just change to BTU per pound mass. Similarly also for H1. Okay. For H1s, okay, if you look at here is 10%. 10%. So you have to refer 10%, 70 degrees C, I think it's around 20 degrees C. Okay. So if you look at here, okay, how to read this table? 10%, around 20 degrees C, I think it's just around here. Okay. Okay, around below 100 something. Okay. So you can get 34 BTU per pound mass. Okay. So you can get 926, okay, 9.262 times 10 power of 6 BTU per pound mass. Okay, this is how you calculate from the diagram. Okay, how much the solid soluble in solid. Okay, so that's how you calculate. You determine the heat. Okay, from the diagram. Okay.
Doktor, the diagram kan
Uh-huh.
nanti dia dekat test tu given ke ataupun kita search kat appendix, sebab appendix tak ada kan?
Appendix tak ada? No, it's not in the appendix. It page
Ah,
462, I think. 462, 465, page 465. There's not in the appendix.
400.
465.
Oh.
Okay.
Okay.
Page, yeah, chapter 12. Okay.
Dekat buku baru tu tak ada, doktor.
Tak ada?
Tak ada.
Are you sure?
Yeah, buku baru page lain saya rasa.
Page lain, yeah.
Buku baru yang ni, itu chapter 11.
Oh, in chapter 11.
Eh,
So you have to refer to chapter 11.
tapi tak complete.
Oh, tak complete. It's already changed, I see.
Oh. Dan kalau buku baru saya ada jumpa ni doktor, H2SO4.
H2SO4. How about NaOH?
Kat page 407. Kalau NaOH dekat NaOH, yap. Tak ada.
Tak ada? Ada, saya rasa.
Tak ada.
NaOH tak ada.
Tak ada. Ha.
Okay, it's okay.
Alright.
If not given, we will provide for you for the test.
Okay.
Okay. So, but please check again. Is it available or not? Okay. So, and just confirm with me if the diagram is available. Okay.
Okay, doktor.
Okay. So another thing is if is not HX diagram is not available, actually we can calculate delta H mixing from the heat of the solution. Okay. Generally, the symbol of delta H solution is something like this. Okay. This is mostly for the lithium chloride. Okay, delta H. solution. The symbol there is a long, I think it's a long hair here, long bar. Okay, this is the delta H of solutions. Okay, for examples like a solid or gas are dissolved in the liquid. Okay, so the heat effect is, we call it as the heat of solution. Okay, so and generally the heat of solution is based on the dissolution of 1 mole of solute. Okay, so that means if species 1 is the solute, then the is soluble in the solutions. Okay, we can calculate the heat of solution per mole of the, generally solute per mole of the solution. Okay, heat of solution is a basis of the mole of the solute lah. Okay, nanti kita akan tengok macam mana. Okay, so this is the symbol. Okay, so to calculate, for example, this one is for the lithium chloride, right? Okay, lithium chloride. Okay, for the lithium chloride in the solution of 12 moles of H2O. Okay, 1 mole of the solute. This is the solute. Okay, okay, this one is the solution. Okay, so that means solute in the solution. Okay, how much the heat of the solution. Okay, so to see this how much the heat solution, you can just refer into figure 12.114. Okay, figure 12.14 is this figure. For example, where's the figure 12.14? I think I forgot earlier. This one is figure 12.144. Okay, so that means total is 12 mole, right? Okay, and mole of H2O per mole of solute. If you refer the equations, okay, this one is 11, this one is 11, 12, right? So this is lithium chloride. Okay, 12 of mole solution. Okay, H2O. Then we can calculate this one. 31, 32, 33, right? Around 33.5. Okay, 33.5 kilojoule, 0.5 kilojoule. Okay, so you can refer that. So moles of H2 is 12. You look at here, and then solute is 1 mole. So solute lithium chloride. Okay, so it's, see, almost right. So we can calculate from the graph. Okay. Actually, you can refer. No. Okay. So this is, you can refer to the figure 12.114. Okay. So delta H mixing you have to times with the solute. Okay, and so solute. Okay, with delta H of the solution. Okay. So that is for the lithium chloride. Okay, and from the heat formation also is possible. How to calculate? Okay, so this one is actually is based on the, if you look at the page 457 actually. Okay, for the 12 mole of H2O, lithium chloride in 12 mole of H2O. This is the heat of formation. From the heat formation, you can calculate heat of solution. Okay, so if you look at here, how they calculate. Okay, if you look at here, if you refer to page 457, okay, 457 is there is a heat for the lithium chloride in 1 mole of H2O, lithium chloride in 2 mole H2O, until lithium chloride in 15 mole of H2O. So you can refer here. Okay, so this one is for only for lithium chloride. Is given the H formation is for -405. Okay, and this one is for the from the graph. Okay, and then we can calculate the heat of formation from the solution. Okay, if you want to calculate heat of solution from the heat of formation, also possible. Okay, so this one, heat of formation, heat of solution from the heat of formation. Okay, so just calculate this one, delta HF and delta HF. This one is from the page 457. So you can get heat of solution. Okay, just almost similar like the heat of reaction. Okay, exactly the aspect is almost like the heat of reaction. Okay, just you draw the equation and then cancel out some of the component, and then you can get the total equation. Okay. Okay. So let's see the example though. Okay, how to apply this one. Okay, all the based on the diagram as well as from the page 457. If you look at here that a single effect evaporator operating at atmospheric pressure concentrate 15%, okay, lithium chloride solution to 40%. The feed enters the evaporator at the rate of 2 kg per second at 25 degrees C. The normal boiling point of a 40% of lithium chloride solution is about 132 degrees C, and its specific heat is estimated 2.72 kilojoule per kilogram. What is the heat transfer rate in the evaporator? Okay, so actually you can refer this one in the example 12.5. This is one of the good example actually showing that we have to draw a hypothetical part, okay, a diagram, okay, before you you solve this problem. Okay. Okay. So this is the diagram. Okay. But you have to determine. You have to do the mass balance first. You want to know the mass exit from the evaporator, right? Okay. If you do the mass balance, so you can determine M1, M2 as well as M3. Okay. Once you do mass balance, okay, what we have to do is we have to do energy balance. Then we want to know the heat, right? Heat transfer. Okay. So if you look at here that from the energy balance, okay, M3 H3 M2 H2, okay, M1 H1, it should be plus this one. Okay. Okay, this one plus. Okay, this is exit, this one and enter. Okay. So what we have to do is we have to do the hypothetical part. Okay, because we only have a heat solution data at 25 degrees C. How about this one, 132 degrees C? How can we determine this one? That's the problem. Okay, we only have data at 25 degrees C. Okay, so if we do the hypothetical part here, okay, if you look at here, okay, look at here, this is your, actually this is your evaporator, right? Okay, okay, you enter here and then separated the feed into pure species. Okay, and then 0.30 kilogram, okay, is mixing with the 0.5 of the water. Okay, and the rest is go to as a superheated steam. This is the become superheated steam. Okay, 1.225. This is what you calculate from the mass balance. Okay, similarly, also this is what you calculate from the mass balance. That's why 0.5. The rest of 0.5 is mixed with the 0.3 of the lithium chloride. Okay, so this is unmixing process HA. This is mixing process. This is heating of the solution. Okay, heating of solution actually change in temperature from 25 degrees C to 132 degrees C. Okay, so you have to use, what is it? Okay, sensible heat equation, because change in temperature. Okay, sensible heat. So you need Cp heat capacity. Okay, so this one you can calculate. Okay, once you do the hypothetical part, you know the stage how to calculate enthalpy, HA, unmixing, mixing, sensible heat as well as superheated steam. Okay, so you can get total delta pH. Okay, so this one is just from the steam table. This one is from sensible heat. This one is you can use a diagram. Okay, diagram or yes, diagram, HI diagram. Okay, or from the page 457 as well as from the appendix C4. Okay, okay. So if you look at here in generals, okay, HA, HB, HC, HD. Okay, based on this one, HA. This one is HA, HB, HC, and HD. Okay. So look at here, HA mole entering. So just calculate the mole entering. Okay, you can get the, for the water is 94, and for the lithium chloride is 7. Okay, mole lithium chloride per second. Okay, and you calculate the number of moles, total moles. Okay, you can get the 13. Okay, and delta H mix from the figure 12.14. Okay, so that means 12.14. Okay, 12.4 is this one. This one is 30 more, right? 1, 2, 3, around here. Okay, total is 30 more. Okay, so we can calculate around 33.8 thousand. Okay, 33.8 kilojoule per kilojoule per mole of solid. Okay, that one is for HA. Okay, and then for the mixing process HB, this one mixing. Okay, if you remember, this one is the mixing. Enter the reactor 0.5 and 0.3. Okay, just calculate number of mole for the lithium chloride and number of mole for H2O, and determines the N bar. Okay, this is to, we want to refer to table 12.14. Okay, just around 3.5 mole. Okay, similarly you have to do the vertical and horizontal lines, so we can get negative 23.2 kilojoule per mole of the solid. Okay, okay, so after that we can get delta HB, okay, times with the 7.7 mole of lithium chloride. Okay, okay, for the heat of solutions, this is change in temperature. Okay, look at here, 25 degrees C to 132 degrees C. Okay, so we have to use sensible heat, MCP delta T. Almost enough already, because the pressure I think is very low. Okay, pressure is low, and then 25 to 132 degrees C is not really difference. 132 to 25. Okay, you can get sensible heat. Just MCP delta T, as well as for the HD. Okay, HD is from the steam table. Okay, if you calculate from the steam tables, okay, we can get H out as well as H in. Okay, so we can calculate delta H. Okay, so similarly also actually this one, it said you can calculate by using a Riedel. Okay, that means from the saturated liquid to saturated vapor. Okay, so saturated, this one 25 to 100 is liquid. Okay, and this one is the vapor. Okay, so that means that is a liquid. Vapor minus liquid. Okay, so radial is change in phase. You have to remember that. Okay, how to calculate? This one is we call it as a latent heat. Okay, latent heat, change in phase, but no change in temperature. Okay, so this is the outlet. Okay, and then you just add all the value, so we can get the total Q. Okay, so this is this one is for HA, HB, HC as well, HD. This one is a sensible, this one is latent heat, this one heat of mixing. From the figure 12.14 for the lithium chloride, okay, as a solute in H2O. Okay, so you have to remember that. Okay, so I hope this one is clear. Any question about this one? So I think it's quite complex, okay, because you have to consider many things. Okay, mixing, and then change in temperature, change in also change in also in what else? Change in phase. Okay. Okay. Okay, so let's move. Okay, I think this is the last. Okay, let's redo tutorial this one. If lithium chloride 2H2O, okay, in 2 mole of H2O and H2O liquid mixed isothermally at 25 degrees C to form a solution containing 10 mole of water for each mole of lithium chloride. What is the heat effect of the solution? Okay, so what you have to do is you have to know the equation. Okay, so look at here. Okay, how to do the equation, this one. This one. Okay, what is the reaction? If lithium chloride in 2 mole H2O and H2O mix, okay, is mixed containing 10 mole of water for each mole of lithium chloride. Okay, so if you want to do the overall equation, lithium chloride, okay, the 2H2O, okay, plus H2O. This one is water, right? Later, liquid. Okay, lithium chloride. Okay, in 10 mole of H2O. Okay, so this is the overall equation. Okay, but how can we determine the heat? Okay, how can we determine from the overall equation? So what you have to do, you have to calculate from the heat of formation. Okay, from heat of formation of the solution. You have to remember that. What you have to do is you have to refer to table C4. Okay, if you look at here, this is please refer to the WhatsApp. This is I'm not sure for the new books. Okay, but you have to refer to this one. Okay, to determine. This is from page 457. Okay. Okay. As well as table C4. Okay, table C4. Table C4, this one. Okay. There is a lithium chloride, right? Okay. That one. Okay. Okay. So you have to calculate heat of solution before you can get the heat effect of the per mole of the solution from the heat of formation. Okay. So how can we calculate this one? Okay. So what you have to do is please refer to the WhatsApp. Okay. You have to do the heat of formation. Okay. Just like a heat of reaction, right? So just like a heat of reaction. Okay. There. Okay. So please refer to the WhatsApp. Okay. So there's a reaction 1, 2, as well as 3. Okay. So from the page 457, as well as table C4, can you find the delta H formation? That one. Okay. You can refer also to the what is it? To my WhatsApp. Okay. There's a already given already for you. Okay. Please refer. Can you determine? Given to you the okay. So if you look at here, lithium chloride. Let's do together. Lithium chloride 2H2O. Can you determine? Jadi saya panggil satu nama. Option number 1. Okay, and then lithium plus setengah Cl plus low H2O. Okay, lithium chloride. Okay, so H2O. Ini question number 2. This is question number 2. And then 2 H2 plus lithium H2O. Okay, O2 plus H2O. Okay, question number 3. Okay, so you can get overall equation. So delta H1, delta H2, delta H3. Can someone? Delta H1, what? What is the value? Delta H3 is what value? Siapa dia ni? Only 24 participants. Okay. Nila? Nila ada Nila. Okay. Dan delta H. Buat campurkan semua. Add all this heat of the formation, you can get delta H. And then since we have 11 mole of the solution, so if you look at here, lithium chloride, okay, dot 2 H2O, okay, plus 8 H2O times lithium chloride H2O. Okay, so this one is based on the 11 moles of solution. Okay, if you look at here, this one, right? This one is at 1 mole of lithium chloride. This one is 10 mole of water. So total is 11 moles. Okay, 11 moles. So you have to divide delta H, divide by 11 moles. So you can get, okay, in 1 mole of the solution. 1 mole of solution. Okay. Inilah, dapat tak? Inilah. Ramadan? Delta H1. Not anyone? Okay. Oh, ada chat ya. Okay. Different Dr. in the new book. This is chapter 11. Okay, so you have to refer to chapter 11 for the new books. Okay, I'm not sure. Lukman Hakim. Okay, but the most important thing is about the heat mixing. Okay, chapter 11. New book is chapter 11. Yes, Doctor. 465. 465. Okay. Okay. All book is a 465. Ramadan, can you get? Who else? Mana yang lain? Who's reconnecting ni? Okay. Nampak tak? Anyone? Okay. Delta H101. Yes, delta H1012650. So delta H is equal to, where's the, okay, it should be, because this one, right, is opposite side. Okay, it's going to be opposite side, so it's going to be positive. negative, okay, time negative 1012650 joule, okay, times. So it's become positive, this one. Okay. So how about delta H2? Okay. As well as delta H3. Okay, for delta H3, you have to remember this one we have to times with 2. So this one also you have to times with 2. Okay. Ada dapat? Siapa? Nila tak ada lagi. Nila tak ada jawapan lagi. H2 is H2 241. I don't think so. Okay. So if you refer to, yes, delta H2 is a negative 441. Okay. Negative 441 5579 joule. Okay. Delta H2. No double. Yes. Sorry. 79. Okay. This one you determine from page 457 or in chapter 11. Okay, you just refer to my WhatsApp. So this one is from the tables, this one is from table C4 also. Okay, so if you look at here, this one is water for liquid. So if you look at here, that is a 28 5 5830. Is it correct? I'm not sure. Yes. Okay. So just sum all this value for H1 H2. So you can get delta H as well as this. This one is for 11 moles, and then for 1 moles of the solutions you have to divide by 11 moles. So you can get the answer. So please find the final answer. Okay, faster. It's almost 3 o'clock. Another one example. Why H3 no need times? No need times. No, you have to times with 2. This one. This one is from original data. You have to times 2. Okay. Negative 28. Okay. This one. Negative 28. Okay. Because the formation is H2 plus 2 plus O2, we can form H2O. This one is from this direction. This one is this direction. This one is this direction. Should be the value is original. Negative 285. Okay. 830. Doctor, for delta H must times with 11. Why must times with 11? Divide. You have to divide this one. Divide 11 for 1 mole. Okay. If you want to present in 11 mole also okay. But generally heat of solution is for 1 mole. For 1 mole of the solution. This one. Okay. Generally for 1 mole of solution. Okay. So that means this one you have to divide by 11. Once you determine this one, you can get negative. Okay. Based on definitions, okay, heat of solution is based on the basis of the mole of the solid. Okay, that means based on the per mole of the solution. Okay, delta H of solution. Okay, delta H is equal per mole of solution. That means one mole. Okay, everything is per mole, 1 mole. Okay, so they have to divide by 11. So if this one is 10 moles, this one is 1 mole, so you have to divide by 9. Okay. Okay. So your answer is 0.54. No, the answer is kilojoule. 2, 3. 1, 2, 3. Should be negative. Yes, this one. Negative 53.55 joule. Okay, this is the answer. Final answer. After you divide by 11 mole of the solution. Okay, so let's we move to the question number 2. Last, it's already 3 o'clock. 5 minutes, 50 minutes, 5 minutes. Okay. A liquid solution of lithium chloride in water, okay, contains 1 mole of lithium chloride and 7 mole of water. If 1 mole of lithium chloride in 3 mole of water is dissolved isothermally in the solution, what is the heat effect? Okay, almost similar. Okay, so what you have to do, you have to know the overall equation. Okay, so to get the overall equation and to calculate the heat of solutions, you have to calculate from the heat of formation. Okay, look at here. This is what I did. Okay, just refer to the things to the WhatsApp. Okay. Okay, so that is the equation. Lithium chloride in 3 mole of H2O. Okay. Produce lithium actually is the opposite direction. Okay, and then for the water, reaction number 2. And then for the motion of lithium chloride in 5 mole of H2O is equation 3. And lithium chloride times plus with the Cl2, okay, plus with the 7 mole of H2O. Okay, so we can get a lithium chloride in 7 mole of the H2O, but this one also the opposite side for the equation number 4. Okay, so please, it consists of four equation, right? Okay, before you get the final equation. Okay, lithium chloride in 7 mole of H2O plus with lithium chloride in 3 mole of H2O to produce 2 mole of the lithium chloride. Okay, in 10 mole of the H2O. Okay, so what's the answer? Okay, please do. So if you look at here, from the equation, delta H1, delta H2, delta H3, delta H4. H. Okay, that's the answer. Okay. So this one is from tables. This one is from table C4. This one is from page 4, 5, 7. Okay. So this one you can determine directly. You can determine directly. This one is directly. The problem is this one, H4. How can you determine this one? Okay. Based on the page 4, 5, 7. How can you determine this one? Okay, what you have to do, if you look at here, lithium chloride, okay, 5 H2O, okay, and then lithium chloride 7 H2O, okay, lithium chloride 8H2O. Okay. So what you have to do, you have this one, this information kan. This one you don't have the information. Okay. This one what? Okay, this one is to refer to page 457. Okay, or from the data I given. Okay, negative 436. Okay, 807 805 joule. Okay, and this one negative 440.529 joule. Okay, how can we determine this one? Okay, any idea? Because it's not given, right? Any idea? Okay, Farhan Rivanza. How can we determine this one? Interpolate, yes, interpolation. You have to do interpolation. If you do the interpolations, okay, if you do the interpolation, this one is x1, x2, x3. This one y1, y2, y3. Okay, so you have do the interpolation. Okay, so y2 go to x1, x2 minus x1, y3 minus y1 divided by x3 minus x1. Okay, plus y1. Okay, this one is x1. Okay, so you can get y2. This one. Okay, so you can get this one, h4. Okay, good job. Okay, so after that you can add all the heat. Okay, so delta H go to delta H1 plus delta H2 plus delta H3 plus delta H4. Okay, so you can get delta H. Okay, okay, so you can get delta H. Okay, any questions? So the answer is gonna be 9. Okay. Okay, any questions? Actually, we end of our chapter 12 before we end our class. Ada soalan tak? Clear kan? No, doktor. Okay. Okay, so kalau tak ada soalan, okay, if you're not satisfied with the test ones, okay, we can discuss again, or I can check again your answer. Okay, for those who have lower marks, but average actually is I'm satisfied with your performance actually. Most of you get more than 90%. Okay. Okay. Only the for those who didn't get the 100% is because of your question 1B. Okay. The way you discuss. Okay. The way you discuss actually. Okay. I just minus 1. Okay. Actually from your actual data. Okay. Actually from your calculation. From the ideal gas as well as Radikong is not rupture, but from van der Waals is rupture. Okay, but from the actual data, actually your container is not rupture. So that means if based on the calculation ideal gas as well as the Reddit quants, your what is it? Your container is not ruptured. Okay, based on the actual data also. So the main conclusion is your container is not ruptured. Okay. Okay.
Okay, Doktor.
Okay. If so, we end our class today, and next week we will move to the chapter 10. Do not forget to do your assignment. Okay, chapter 11 as well as this new assignment. Okay, please submit. I'm not sure. I don't. For the chapter 11, I don't remember when is the deadline. Okay. Have you submitted the chapter 11 assignment? Not yet. Hari Ahad holiday kan? Ahad holiday. Holiday apa? Holiday.
Holiday aja.
Sultan Terengganu. Holiday ke?
Terengganu holiday lah.
Saya je lah cuti.
Is it cuti Saya check. Saya check jap. Johor holiday.
Awal Ramadan.
Ya ke? Awal Ramadan besok.
PKP tak valid ke?
Awak ni pada pandai je. Holiday ke? Saya rasa tak ada kan? Johor holiday. Sekejap